The aircraft rolls to a stop on the flight line, and the sound changes. Not immediately. The engine does not simply switch off. It spools down. The high, hard whine that filled the flight line as the aircraft taxied in begins to fall through its frequencies, descending from the pitch that is felt in the chest to the pitch that is heard normally to the pitch that is barely heard at all. The turbine stages decelerating through their characteristic sound signatures as the fuel cuts and the rotating machinery loses its driving energy and begins to coast. The process takes a minute or more for a large engine. You can hear it ending. The ground crew are already moving. They were positioned before the aircraft arrived, marshalling the jet into its parking spot, chocking the wheels the moment the aircraft stops, so connecting the grounding cable that prevents static discharge from the aircraft's skin from becoming a problem near fuel. One of them climbs the boarding ladder that has been rolled into position before the canopy is fully open. If this kind of story is how you end your nights, please subscribe right now so you never miss one. Hit the like button. It helps this channel reach more people enormously. And drop a comment telling us where in the world you are watching from and what time it is there. We love knowing who is out there. Now, let's go to the flight line. The pilot climbs down. They have been in the aircraft for however long the mission required. An hour, 2 hours, sometimes considerably more on long-range sorties with air-to-air refueling. The cockpit of a fighter jet is a small, enclosed environment shaped entirely around the requirements of the mission. The instruments and displays positioned for rapid scan. The controls accessible without reaching. The ejection seat behind the pilot filling the remaining space with its mechanisms. After hours in that environment, stepping down onto the concrete of the flight line and standing upright in the open air is a specific physical relief. The aircraft settles into stillness around them. The fighter jet at rest does not look like a machine at rest. It looks like a machine waiting. The swept surfaces and the blended shapes of a modern stealth fighter have no component that does not serve a purpose. Every curve and every angle is the product of aerodynamic or radar signature requirements that were worked out over years of design and testing. And sitting motionless on the concrete, the aircraft retains the visual quality of something in motion. The lines running from the intake edges to the tail, the wing surfaces angled against the sky, the whole form designed for the air rather than for the ground. The sun is finishing. The flight line lights are coming on. The aircraft that flew today are in their spots, their engines cooling, the maintenance crews beginning the work that will have them ready for tomorrow. The last sortie is done. The day's flying is finished, and the aircraft stands on the concrete in the gathering dark, waiting for whatever comes next. A jet engine does 4 things in sequence, and it does all 4 of them continuously, simultaneously, and at a rate that produces thrust measured in tens of thousands of newtons. The first thing is intake. Air enters the engine through the intake at the front. In a fighter jet, the intake is carefully shaped to compress the air slightly and to manage the airflow at the specific speeds the engine will encounter. From the slow approach to landing to supersonic cruise, where the air arriving at the intake face is moving faster than sound. The intake manages this entire speed range with geometry, ramps and cones, and carefully calculated duct shapes that slow the supersonic airflow to subsonic before it reaches the compressor, because the compressor cannot work efficiently with supersonic inlet flow. The second thing is compression. The compressor, a series of rotating disc stages, each one a ring of precisely shaped aerofoil blades that accelerate and then decelerate the air, raising its pressure at each stage, multiplies the air pressure by a factor of 25 to 30 in a modern high-performance engine. Each stage adds a modest pressure ratio. The stages multiply together. The air entering the engine at atmospheric pressure leaves the compressor at 25 atmospheres or more, hot from the work done on it, dense, energetic, ready for combustion. The third thing is combustion. Fuel, typically aviation kerosene, Jet A, or its military equivalent, JP8, is injected into the compressed air and ignited. The burning raises the temperature of the gas dramatically, from approximately 600 degrees Celsius at the compressor exit to perhaps 1,600 degrees Celsius at the turbine entry in a modern high-performance engine. The hot, high-pressure gas wants to expand, and the only place it can go is rearward through the turbine. The fourth thing is expansion through the turbine and nozzle. The turbine extracts exactly as much energy from the expanding gas as the compressor needed to do its work, no more and no less. The turbine is connected to the compressor by the central shaft, and the turbine blades are shaped to extract the right amount of work from the gas passing through them. After the turbine, the gas, still hot, still moving fast, but now at lower pressure, accelerates through the nozzle and exits the engine at high velocity. This high velocity exhaust is the thrust. The efficiency of this cycle, the Brayton cycle, the thermodynamic framework that describes gas turbine engines, improves as the temperature ratio across the cycle increases. Higher turbine inlet temperature means more work extracted, means more thrust per kilogram of fuel burned. The limiting factor is what the turbine blades can survive. The first turbine stage in a modern fighter engine operates at gas temperatures that exceed the melting point of the metal the blades are made from. The blades are kept below their melting point by internal cooling channels that flow cool air from the compressor through the blade material. The same principle Goddard used for the rocket combustion chamber. Air in, compressed, burned, expanded out, continuously, at temperatures that should destroy the metal, kept from doing so by the air flowing through the metal itself. After the turbine, there is still fuel left to burn, not deliberately left. The combustion in the main engine is thorough, at the fuel-to-air ratio managed carefully to ensure complete combustion within the temperature limits the turbine can survive. But the turbine requires that fuel ratio to be kept below the stoichiometric limit, the ratio at which all the oxygen in the air is consumed. The turbine cannot tolerate the temperatures that complete combustion would produce. So, the engine runs fuel lean, and the exhaust leaving the turbine contains roughly half of the oxygen that entered the intake. Half the oxidizer potential of the ingested air passes through the engine unused. The afterburner uses it. The afterburner, called reheat in British usage, is an extension of the engine's exhaust duct, positioned aft of the turbine, in which additional fuel is injected directly into the hot exhaust stream and ignited using the remaining oxygen. The exhaust temperature rises again, from perhaps 800 degrees Celsius as it exits the turbine to over 1,700 degrees Celsius in the afterburner. The reheated gas expands through a variable area nozzle, the petals at the rear of the engine that open when the afterburner is lit to accommodate the increased volume of the expanded gas. The thrust increase from the afterburner ranges from approximately 40 to 70% for modern turbofan engines. This is not free. The fuel consumption triples. The operational time on afterburner is limited by fuel availability. At full afterburner, a fighter jet's fuel state declines rapidly, and the pilot keeps careful count of the minutes. The visual signature of the afterburner is the shock diamonds. When the exhaust exits the nozzle at supersonic speed, the gas overexpands and then recompresses in a repeating cycle. The pressure oscillates as the exhaust plume adjusts to the ambient atmospheric pressure. These oscillations produce a series of bright, diamond-shaped regions in the plume, where the compression raises the temperature to visible incandescence. The diamonds bright against the darker regions between them, the pattern repeating down the exhaust cone like a luminous necklace. The number and spacing of the diamonds is determined by the pressure ratio across the nozzle exit and the ambient pressure. They are visible at night from kilometers away. Lighting a match while it is attached to the side mirror of a car traveling at highway speed. And that is how one engineer at Pratt & Whitney described the challenge of afterburner ignition: maintaining a stable flame in an airstream moving at several hundred feet per second. The flame holders, ring-shaped structures in the afterburner duct that create zones of lower velocity where the flame can anchor, hold the combustion steady in a flow that would otherwise blow it out. The engineering is not elegant to describe. The result at night from the ground is extraordinary to see. The nozzle opens, the fuel flows, the diamonds appear, and the aircraft accelerates into the dark. Mach 1 is not a wall. This needs saying because the language that surrounded the sound barrier in the 1940s. Barrier, wall, the implication that it was a physical obstacle that might not be crossable, created a misconception that has lingered. The sound barrier is a transition, not a boundary. On one side of it, the aircraft is moving slower than the pressure waves its own motion creates in the air ahead. Those waves propagate forward, pushing air out of the way before the aircraft arrives. On the other side, the aircraft is moving faster than those pressure waves, which means the air ahead receives no warning of its approach. The aircraft arrives before the information about its arrival does. The transition has real physical consequences. As an aircraft approaches Mach 1, the air ahead of it cannot move out of the way fast enough, and a compression, a shock wave, forms at the nose. The shock wave is a very thin region of rapid pressure and density increase. The air in front of the wave at one pressure, the air behind it at a much higher pressure, and the transition happening in a distance of a fraction of a millimeter. The drag associated with forming and maintaining this shock wave drag, increases steeply as the aircraft approaches and crosses Mach 1. Early jet aircraft encountered this wave drag rise before their engines had enough thrust to overcome it, which is why the sound barrier seemed impassable. It was not a physical barrier, but an engine thrust deficit. Above Mach 1, the shock wave sits at a fixed angle behind the nose, and the wave drag stabilizes. The aircraft is now in supersonic flow, the physics different from subsonic in specific and manageable ways. Mach 2, twice the speed of sound, approximately 680 meters per second at altitude, where the speed of sound is somewhat lower than at sea level, is achievable by aircraft with sufficient thrust-to-drag ratio, as the F-22 can exceed Mach 2. Above Mach 2, a new constraint appears: aerodynamic heating, At these speeds, the compression of the air ahead of the aircraft raises its temperature, and this heat conducts into the aircraft's structure. The aluminium alloys used in most aircraft structures begin to lose strength at elevated temperatures. The SR-71 Blackbird, which cruised at Mach 3.2, was built primarily from titanium, because aluminium would have softened at the temperatures its skin reached. The aircraft expanded several inches in length during cruise. The titanium panels, deliberately designed with gaps between them on the ground, that closed as the aircraft heated to operating temperature. At Mach 3.2, the outside temperature of the airframe was over 300 degrees Celsius. At Mach 6, where experimental hypersonic vehicles operate, if the temperature rises above 1000 degrees Celsius, the atmosphere resists. The higher the speed, the harder it resists. Every Mach number above 1 is bought with heat and with the engineering required to manage it. The F-22 Raptor can fly faster than sound without the afterburner. This capability, called supercruise, is among the most significant performance attributes of the aircraft, and it is worth understanding what it means in practice. Every other supersonic aircraft flies supersonically on afterburner, which means every other supersonic aircraft burns fuel at 3 times its dry rate while doing so. Supersonic flight with afterburner is fast and extremely expensive in fuel, which limits the time that can be spent at supersonic speeds on any given mission. The F-22, using its 2 Pratt & Whitney F119 engines at full military power without afterburner, sustains supersonic flight at approximately Mach 1.5, fast enough to close distances rapidly or to escape engagement, without the fuel penalty that makes supersonic flight so operationally costly in other aircraft. The F119 engines that make this possible were, until the F-35's F135 entered service, the most powerful turbofan engines ever fitted to a fighter aircraft. The F-22 carries 2 of them, and their combined thrust gives the aircraft a thrust-to-weight ratio above 1, meaning the aircraft can accelerate vertically, climbing straight up while gaining speed, which no amount of aerodynamic cleverness can substitute for in a close-range engagement where energy management is everything. And the thrust vectoring nozzles are the other performance feature of the F-22 that distinguishes it from every other Western fighter. The nozzle at the rear of each engine can pitch up or down by 20 degrees, a seemingly modest range that translates into an enormous control authority at the edge of the aircraft's flight envelope. At very high angles of attack, where the conventional control surfaces, the rudders, the ailerons, are operating in disturbed airflow and generating reduced effectiveness, the thrust vectoring nozzles continue to work. The aircraft can point its nose in directions that conventional aircraft cannot. The thrust redirected to change the aircraft's orientation, even when the aerodynamics would otherwise not cooperate. Since the F-22's service ceiling is officially listed as above 50,000 feet, the precise number is classified. At that altitude, the sky above the aircraft is already the dark blue-violet of the stratosphere. The air is 1/10 as dense as at sea level, and the aircraft is above the operational ceiling of most of the missiles designed to engage it from the ground. The curvature of the Earth is perceptible at the horizon. 187 F-22s were built. Production ended in 2011, a decision that has been debated ever since. the aircraft has never been exported. Federal law prohibits its sale to any foreign government, a measure taken to protect the classified technologies it carries. It remains the only operational Western fighter with thrust vectoring. 2 engines, supercruise, thrust vectoring, a ceiling where the sky is already dark, the most capable pure air superiority aircraft ever to fly. Waiting, currently, for a mission that may never require everything it can do. Stealth is not invisibility. This distinction matters for understanding what stealth aircraft actually do, and why they are built the way they are. An invisible aircraft would not show up on radar at all. There would be no return, no indication of its presence. A stealth aircraft is not invisible to radar. It returns a radar signal that is dramatically smaller than a non-stealth aircraft of the same size. Small enough that the return is difficult to detect, difficult to track, and difficult to build a targeting solution from at operationally useful ranges. The difference is one of degree, not of kind. Radar works by transmitting electromagnetic energy and waiting for it to bounce off targets and detecting the returned energy. The power of the returned signal depends on the target's radar cross-section, a measure of how effectively the target reflects the transmitted energy back toward the receiver. A large airliner has a radar cross-section of perhaps 100 square meters. The F-16, a conventional 4th-generation fighter, has a radar cross-section of approximately 5 square meters. The effective reflecting area is much smaller than the aircraft's physical size, because most of the radar energy is scattered in directions other than back toward the receiver. The F-22's radar cross-section is estimated at approximately 0.0001 to 0.0005 square meters, often compared to the size of a marble. 2 design approaches produce this reduction. The first is shaping. A flat surface perpendicular to the radar beam returns almost all the energy directly back to the receiver. It is the worst possible geometry from a stealth perspective. A swept, curved surface scatters the radar energy in multiple directions, most of them not toward the receiver. The blended surfaces of a modern stealth fighter, the continuous curves, the edges that are aligned at specific angles, the absence of any right-angle features, are designed to ensure that the radar energy transmitted at the aircraft is reflected away from the transmitter rather than back at it. The second approach is radar-absorbent material. Certain materials, ferrite-loaded composites, carbon-based materials, absorb electromagnetic energy at radar frequencies rather than reflecting it, converting the radar signal to heat. These materials coat the surfaces of stealth aircraft, absorbing what the shaping does not scatter. They require maintenance. The coatings chip and degrade, and must be inspected and repaired between missions, a significant part of the logistics cost of operating stealth aircraft. Internal weapons bays are a third stealth requirement. A conventional fighter aircraft carries missiles on external pylons under the wings. The pylons and the missiles themselves are large, angular objects with substantial radar cross-sections. A stealth fighter carries its weapons internally, the bay doors closed and flush with the fuselage skin until the moment of release. The sum of these measures produces an aircraft that can approach adversary radar systems significantly more closely than a conventional aircraft before being detected. Not invisible, just very, very hard to see, until it is too late to matter. every critical control in a fighter jet cockpit can be reached without the pilot's hands leaving the stick and the throttle. This is the hot-ass principle, hands on throttle and stick, and it represents a fundamental design philosophy about what a fighter pilot should and should not need to do during the demanding phases of flight where attention cannot be divided. In a high-G maneuver, in a merge with an adversary aircraft, in the seconds of the weapons envelope, the pilot cannot afford to look down at the instrument panel and reach for a specific switch. The critical controls, weapons system management, radar modes, radio communications, and defensive systems are positioned on the throttle and stick grip in configurations that experienced pilots operate by feel without looking. The cockpit itself is built around the pilot's body in a reclined seat position. The angle of recline varies by aircraft, but 15 to 30 degrees is typical for modern fighters. The seat tilted back to improve the pilot's G tolerance by shortening the distance from heart to brain and reducing the effect of blood pooling in the lower body during high G maneuvers. The instrument panel is close enough to read without leaning forward. The canopy provides the widest possible field of view. The bubble canopy of the F-16 offering nearly unrestricted vision to the sides and rear. The pilot able to check for threats at the 6 o'clock position without requiring any external sensor. And the helmet-mounted display projects critical flight data: airspeed, altitude, weapons status, targeting cues, onto the pilot's visor, visible regardless of where they are looking. In an aircraft with a helmet-mounted sight, the pilot can designate a target by looking at it. The missile seeker head slaving to the direction of the pilot's gaze and acquiring the target without the aircraft needing to point toward it. The G-suit is worn over the flight suit, covering the legs and abdomen in bladders that inflate automatically when the accelerometer detects G above approximately 2. At high G, the suit inflates firmly, pressing on the lower body and legs to resist the pooling of blood away from the brain. Without it, consciousness would be lost in a high G turn in seconds. With it, and with the AGSM, the anti-G straining maneuver saw a specific combination of muscle tension and breathing pattern that pilots train and practice. A modern fighter pilot can sustain 9G for several seconds. The ejection seat is the last resort. The Martin Baker seat, used in most Western fighters, fires the pilot clear of the aircraft using a rocket motor, the seat continuing to fire for a fraction of a second after it has cleared the canopy, slowing by parachute above a minimum altitude and providing survival equipment for the pilot's situation after landing. The 0-0 capability, the ability to eject safely from a stationary aircraft on the ground, has saved lives that earlier seat designs could not have reached. The cockpit is a very small world. It contains everything the pilot needs, and nothing they do not. At 9G, the human body weighs 9 times its normal weight. Not feels like, weighs. A pilot of 80 kilograms at 9G experiences the same force on their body as a person of 720 kilograms would feel standing still. The blood in their body weighs 9 times its resting weight and flows accordingly, away from the brain, pooling into the legs and abdomen under the force of the acceleration. The eyeballs, pressed outward in their sockets by the increased weight of the fluid behind them, begin to fail as a visual instrument. The peripheral vision narrows first, the grey curtain that closes in from the outside of the visual field, as the blood supply to the retina becomes insufficient. Then the color drains. Then, if the G is sustained, the visual field shrinks to a narrow central tunnel. Then it goes black. And this progression, from normal vision to grey out to blackout, can happen in 2 to 3 seconds if the G onset is rapid. The brain, following the eyes into oxygen deficit, loses consciousness shortly after the visual field collapses. G-induced loss of consciousness, GLOC, is silent, sudden, and not preceded by any warning the pilot can rely on. The pilot is flying normally, pulls into a high G turn, loses consciousness without any sensation of doing so, and the aircraft continues on whatever trajectory it was following without input. At low altitude, this is fatal. Modern G-suits and the AGSM, the anti-G straining maneuver, saw a specific combination of abdominal muscle tension and a forced exhalation against a closed airway that increases intrathoracic pressure and helps maintain blood pressure to the brain. Allow trained pilots to sustain approximately 7 to 9 G for several seconds. The technique takes months to develop and requires continuous practice to maintain. Pilots who stop flying high G aircraft and return to them find their G tolerance has degraded. 9G is the structural limit of most modern fighters. The maximum load factor the airframe is designed to sustain before the risk of structural failure exceeds acceptable thresholds. The aircraft can pull harder than 9G. The design limits are set with safety margins. But 9G sustained is already at the edge of what the human body can manage, which means the aircraft's structural limit and the pilot's physiological limit coincide approximately, a fact that reflects the design reality that the pilot is the weakest structural element in the system. Below 9G, at the 3 and 4G levels of a sustained turn, the effect is less dramatic but still significant. Breathing is harder, the arms are heavier. Reaching forward to the instrument panel requires conscious effort. Sitting still is comfortable. Moving against the load is work. At 1G, the resting state, the ground, none of this is apparent. The body assumes it is normal. It is what we were built for. The fighter jet was built for the rest of the range, and the pilot is trained to survive it. Energy is life. The phrase belongs to John Boyd, the American fighter pilot and theorist who spent the 1950s and 1960s developing and codifying the energy management principles that transformed how military aviation understood air combat, who refined the concept that in a close-range engagement, victory goes to the pilot who can most effectively manage the conversion between kinetic and potential energy. Boyd was an unusual figure, a tactical innovator who worked largely through the force of argument rather than institutional position, whose theoretical contribution, the energy maneuverability theory, changed the way American fighter aircraft were designed. He would reportedly bet any pilot in the Air Force that starting from a position of disadvantage, he could put himself in a gun-shooting position within 40 seconds. Nobody collected. And the physics behind the principle are straightforward. A fighter aircraft at any moment possesses a specific total mechanical energy. The sum of its potential energy, proportional to its altitude, and its kinetic energy, proportional to the square of its speed. A pilot who converts altitude to speed dives. A pilot who converts speed to altitude climbs. Neither conversion is free. Drag continually dissipates energy from the system, and the engine provides energy through thrust. The pilot's job is to manage the energy budget, spending it tactically in the maneuvers that create advantageous positions, conserving it when possible, and ensuring the aircraft's energy state does not fall below what the tactical situation requires. So an aircraft with a thrust-to-weight ratio above 1, as the F-22 possesses, can do something that aircraft with lower thrust-to-weight ratios cannot. It can sustain energy in a vertical plane. It can pull into a vertical climb and continue to accelerate. The drag of the climb is overcome by the excess thrust. This means the F-22 can convert tactical positions in ways that require no trade-off between speed and altitude. It can climb and accelerate simultaneously, a capability that compounds the advantage of already being at high energy. The F-22's climb rate of approximately 62,000 feet per minute, just over 1,000 feet per second, approximately 300 meters per second, means it can reach 60,000 feet from sea level in roughly 1 minute. An F-35, with its single engine and higher wing loading, climbs at approximately 45,000 feet per minute. Still extraordinary by any civilian aviation standard, but nearly 40% slower than the Raptor in the vertical. The energy management concept extends beyond individual aircraft to the geometry of the engagement. A fighter that is higher and faster than its opponent has more options. It can choose to convert that energy advantage into a weapons solution, or it can choose to disengage, using altitude and speed to create separation. A fighter that is lower and slower has fewer options, and the goal of every maneuver in a close-range fight is to improve your own energy state relative to your opponent's. Energy is life. The pilot who loses it loses options. The pilot who runs out of options eventually runs out of something more than that. The catapult fires, and the aircraft goes from 0 to 165 miles per hour in approximately 2 seconds. The physics of this are not subtle. The steam catapult, the system used on American Nimitz-class carriers and the French carrier Charles de Gaulle, stores energy as high-pressure steam in accumulators below the flight deck and releases it through a piston that runs in a track along the deck's length. The piston is connected to a shuttle, a small fitting that extends above the deck surface and into which the aircraft's nose gear is hooked before the launch. When the catapult fires, the steam pressure drives the piston and the shuttle, and through the shuttle, the aircraft, the length of the catapult track in approximately 2 seconds. At the end of the track, the shuttle releases. The aircraft is on its own. If the aircraft has reached flying speed, approximately 150 to 165 miles per hour, depending on the aircraft type, the ship's speed, and the wind over the deck, it climbs. If it has not reached flying speed, the pilot ejects. The ejection decision is made in the fractions of a second after the catapult releases, before the aircraft reaches the bow of the ship and drops toward the sea. The catapult system can accommodate aircraft up to approximately 45,000 pounds launch weight, a constraint that limits what can operate from a carrier, and one of the reasons carrier aircraft have historically been smaller and lighter than their land-based counterparts. The physical sensation of a catapult shot, described consistently by naval aviators, always of being slammed backward into the seat with a force that briefly makes the instrument panel impossible. Naval aviators call it the controlled crash. The description is not entirely accurate. A well-executed carrier landing is a precisely flown maneuver that requires the pilot to meet extremely tight tolerances of speed, glide path angle, and lateral position at the moment of touchdown. But the description captures something true about the experience. Unlike a land-based aircraft landing, where the pilot flares, raises the nose to reduce descent rate, and settles gently onto the runway, a carrier landing arrives at full descent rate, the aircraft flying all the way to the deck, the hook catching the wire, the arresting system stopping the aircraft in approximately 2 seconds from approximately 150 miles per hour, or the glide path is 3.5 degrees, steeper than the standard 3.0 degrees of an instrument landing approach at a commercial airport. Steeper because the carrier's deck is close to the water, and the aircraft must arrive on a path that does not bring it into the ship's stern. The pilot maintains this glide path using the Fresnel lens optical landing system, the meatball in naval aviator parlance, a system of gyroscopically stabilized lights positioned on the port side of the carrier's flight deck that shows the pilot whether they are above, below, or on the correct glide path. A centered amber ball means on glide path. A ball above the datum bars means high. A ball below them means low. A waved off approach means the landing control officer has determined the approach is unsafe and the pilot must go around. The carrier is moving. In a moderate sea, the deck may be pitching several meters over the wave period, rising and falling as the ship encounters the ocean swell. The pilot is flying a precise approach to a surface that is itself in motion, the target, a 40-foot zone of deck between 4 arresting wires, rising and falling and moving away from them at the carrier's own speed. The aircraft crosses the deck threshold and touches down at full engine power. Not reduced power, full power. The engine is at military thrust at the moment of touchdown, because if the hook misses all 4 wires, a bolter, the pilot needs to be able to fly away immediately without the delay of spooling the engine back up from reduced power. The tail hook, a metal hook mounted on the aircraft's tail that trails behind the aircraft on approach, so it catches one of the 4 arresting wires stretched across the deck. The wire pulls the aircraft to a stop in approximately 90 to 100 feet. The deceleration is approximately 4G, acting forward, the opposite direction from the catapult shot. The pilot, already strapped tightly into the seat, is pressed into the harness rather than into the seat back. The aircraft stops. The engine is at full power. The pilot throttles back. The hook releases, and somewhere behind them, another aircraft is already on the glide path, 3/4 of a mile out, watching the meatball. Night carrier landings are considered the most demanding regular flying task in aviation. Day carrier landings are considered the second most demanding, to read, to, at the acceleration between 3 and 4G over 2 seconds, is directional and violent in a way that the sustained G of a banked turn is not, because it comes on suddenly and completely in the forward direction. The aircraft is still in the hands of the catapult for the 2 seconds, and then it is in the hands of the pilot, and the transition between those 2 states is abrupt. The electromagnetic aircraft launch system, EMALS, replaces the steam piston with a linear induction motor, a track of electromagnetic coils along the deck, energized in sequence to accelerate a carriage that replaces the steam shuttle. EMALS, installed on the Gerald R. Ford class carriers and the Chinese carrier Fujian, applies thrust more smoothly and controllably than steam catapults, with fewer abrupt peaks and the ability to be precisely calibrated to the weight of the aircraft being launched. This controllability reduces structural stress on the aircraft and allows lighter aircraft to be launched without risk of overstressing them. The carrier is steaming into the wind to provide additional airflow over the deck. The jet blast deflectors are raised behind the aircraft. The catapult officer checks their instruments. The pilot runs the engine to full military power. The holdback releases. 2 seconds, 165 miles per hour. And then the sea below, and the aircraft climbing, and the carrier already turning to recover, the next aircraft already on approach behind. In principle, a fighter jet that can connect with enough tankers has unlimited range. In practice, at the limit is not the aircraft, but the pilot. The human body cannot sustain prolonged flight in a fighter cockpit indefinitely. The physical demands of maintaining focus during long transoceanic transits, accumulating fatigue that eventually makes continued safe operation impossible. But the theoretical range limit that the fuel tank imposes is effectively removed by air-to-air refueling, and the history of modern tactical aviation is substantially the history of what became possible once range was no longer the constraint. The two refueling systems used by different air forces represent different engineering philosophies. The probe and drogue system, used by the United States Navy and Marine Corps, most European air forces, and many other operators, equips the tanker with a trailing hose that ends in a funnel-shaped drogue basket. The receiving aircraft extends a fixed or retractable probe from its nose or fuselage and flies it into the basket. The probe seating in the drogue coupling and the fuel flowing when the connection is confirmed. The pilot is responsible for maintaining the precise position that keeps the probe in the drogue against the turbulence and the tanker's own wake. The boom system, used by the United States Air Force, places the control on the tanker side. The tanker extends a rigid boom, a telescoping tube controlled by a boom operator aboard the tanker. And the boom operator flies the boom's end into a receptacle in the receiving aircraft's fuselage. The receiving pilot holds position in a contact envelope marked on the underside of the tanker, and the boom operator does the work of making the connection. The boom can transfer fuel faster than the drogue and is preferred for heavy aircraft that require high fuel transfer rates. The precision of the flying required for either system is significant. In the probe and drogue system, the receiving pilot must maintain their position within a contact envelope, perhaps 3 meters in each dimension, forward and backward, up and down, left and right, while the two aircraft are flying at cruise speed through whatever turbulence or weather conditions exist, often at night, often in cloud, sometimes in combat conditions, where the formation must maintain emissions control and cannot communicate normally. The pilots describe it as the most demanding instrument flying they do. Not because the maneuver is violent. It is not. It requires the gentlest possible control inputs to avoid destabilizing the probe-drogue connection. But because the tolerances are tight and unforgiving, the consequence of losing the connection and having to reconnect is disruptive. And the concentration required to hold position for the minutes needed to take on the planned fuel is entirely consuming. The world record for the longest fighter mission, a B-2 mission lasting approximately 44 hours, a strategic bomber rather than a fighter, but illustrative of the principle, was achieved entirely through air-to-air refueling. The sky has no gas stations. The tanker brings the gas station to the aircraft. The pilot holds their position in the turbulence behind the tanker. The fuel flows, and the mission continues past the horizon. On October 14th, 1947, a 24-year-old test pilot from West Virginia, flying a small orange aircraft, dropped from beneath a modified B-29 bomber over the Mojave Desert, exceeded the speed of sound for the first time in recorded history. Chuck Yeager had broken 2 ribs at a horse riding accident 2 nights before the flight, and had told nobody in the program about it, except his friend and fellow pilot Jack Ridley, who fashioned a makeshift tool from the end of a broomstick so that Yeager could lever the cockpit hatch closed with his good arm. The X-1, which Yeager had named Glamorous Glennis after his wife, was dropped from the B-29 at approximately 20,000 feet and fell under its own weight until Yeager lit the 4 rocket motors in sequence. The aircraft accelerated through Mach 0.96, Mach 0.98, Mach 1.0, and continued to Mach 1.06 before Yeager cut the motors and glided back to Muroc Dry Lake. The flight data was classified immediately. Yeager could not discuss it. The program that produced the achievement had been operating under military secrecy, and the confirmation of the achievement was not released publicly for months. Yeager himself, characteristically understated, described reaching Mach 1 as feeling no different from the supersonic test points just below it. The expected buffeting did not occur, the controls continued to function, and the aircraft flew smoothly through the transition that had seemed to represent a barrier. This is the culture of experimental test flying, not the dramatic risk-taking of popular imagination, but the methodical expansion of the known envelope by increments small enough that each step can be extrapolated from the previous one. Any unexpected behavior identified and understood before the next step is attempted. The test pilots of the post-war American research program at Muroc, later Edwards Air Force Base, flew aircraft to limits that had never been reached, accumulating data that defined the performance boundaries of aviation in the jet age. They did so through a specific discipline: fly one data point at a time, evaluate the data, and only then fly the next. Yeager's contribution to aviation was not the bravery of October 14th, 1947. Though that flight required bravery, 2 broken ribs notwithstanding, it was the decade-long accumulation of skill and judgment that made him the pilot who could be trusted to take the X-1 to Mach 1, recognize any anomaly, respond correctly, and bring the data back. The courage was a prerequisite. The judgment was the thing. He continued flying for the Air Force for decades after 1947. He flew combat missions in Vietnam. He retired from the Air Force in 1975 as a brigadier general. He died in 2020 at 97. He described the morning of October 14th, 1947 as a beautiful day to fly, which, by the records, it was. The wing is the compromise that every aircraft designer makes before they make anything else. A wing optimized for slow-speed flight, a high-lift wing with a large chord, high camber, lots of surface area, produces a great deal of drag at high speed. A wing optimized for high-speed flight, thin, see sharply swept, minimal surface area, produces very little lift at low speed and requires very high landing speeds that exceed what an aircraft carrier deck or a short runway can safely accommodate. The fighter jet designer must find an operating point in the space between these two extremes and accept the trade-offs that come with it. The delta wing, the triangular planform used by aircraft from the Concorde to the Eurofighter Typhoon, is swept so aggressively that the leading edge almost reaches the nose of the aircraft. At supersonic speeds, the swept leading edge stays inside the shockwave that forms ahead of the aircraft, reducing the wave drag significantly. The large area of the delta provides enough lift at high speed. At the disadvantage is at low speed. The delta stalls at a relatively low angle of attack in the conventional sense, which requires delta wing aircraft to land at high nose-up attitudes and high air speeds, demanding long runways and careful approach management. The leading edge route extension, the LERX, the strake that runs forward from the wing root toward the nose on aircraft like the F-16 and F-18, is a different solution to a different problem. At high angles of attack, the strake generates a vortex along its upper surface that spirals backward over the wing, energizing the airflow and preventing the separated, stalled condition that would otherwise occur. The LERX allows the aircraft to maintain controllability at angles of attack far beyond what a conventional wing could manage, an important capability in a close-range maneuvering fight, where the pilot needs to point the aircraft's nose at extreme angles. The variable geometry wing, the swing wing used in the F-14 Tomcat, the Panavia Tornado, the Soviet-era MiG-23, sweeps rearward for high-speed flight and forward for low-speed flight, providing optimum geometry for different phases of the mission without compromise. The mechanical complexity of the sweep mechanism, the pivot, the actuators, the structural provisions for a wing that must carry flight loads in both configurations, adds weight and maintenance burden, which is why variable geometry has largely been replaced in modern designs by fixed wings whose sweep and planform are chosen to perform adequately across the required range of conditions, rather than optimally at any specific one. The F-22's wing is a trapezoid, moderately swept, with a relatively large area for a supersonic fighter. It works well at supersonic speeds, adequately at low speeds, with the thrust vectoring compensating for some of the control authority that the moderate sweep sacrifices at high angles of attack. Every wing is a negotiation between what the aircraft needs to do. No wing can do everything. The designer chooses the trade-offs. The pilot lives with them. Every flight, every phase, every compromise expressed in the air. At 40,000 feet at night, the stars are different. Not in kind. The same stars and the same constellations, the same galaxies, different in character. The atmosphere below the aircraft is dense enough to scatter the light arriving from the stars and planets, and that scattering reduces the contrast between the stars and the sky, and softens their apparent sharpness. Above 40,000 feet in the stratosphere, the atmosphere remaining above the aircraft is thin enough that this scattering is substantially reduced. The stars are brighter. They do not twinkle. The twinkling that makes stars visible at their most familiar is a product of atmospheric turbulence affecting the thin column of air through which starlight reaches the ground. And above most of that turbulence, the effect largely disappears. The stars burn steadily. The horizon at this altitude is not a line. It is a curve. The same subtle curvature visible from the upper decks of a very large ship at sea, but here more pronounced. The visible horizon subtends a larger angle, and the arc is unambiguous. Below the horizon, on a clear night over land. The city lights form a scattered orange-white carpet that stretches to the geometric horizon in every direction. Over ocean, there is nothing below. The water surface is dark, the occasional ship a single bright point. The aircraft carrier a cluster of lights in the otherwise unmarked expanse. Night vision goggles transform this environment. The NVGs worn by military pilots conducting low-level night operations amplify the available light, moonlight, starlight, the ambient glow of distant cities, to produce a usable image of the terrain below. Flying at 500 feet above the ground in full darkness, with NVGs, the terrain is visible in green-tinted detail. The hedgerows and roads and rivers identifiable, the obstacles trackable. Without them, at 500 feet in darkness over unfamiliar terrain, the pilot is entirely dependent on the radar altimeter, telling them how many feet of air remain between the aircraft and the ground. The night carrier landing is the combination of all of these demands simultaneously. The precise glide path, the moving deck, the meatball reference, the instrument scan, the darkness that removes the visual depth cues that make the approach feel manageable, the sea that provides no reference for the horizon at all on an overcast night, when the boundary between the dark water and the dark sky is invisible. Naval aviators who have done both describe the night carrier landing as a qualitatively different experience from the day version. Not more difficult in the same way, but different in kind. The aircraft crosses the threshold. The hook catches. The engine is at full power. 2 seconds. Stop. Done. And outside the cockpit, the night over the ocean is exactly as it was before. Dark and moving and vast. The carrier goes on. The aircraft is aboard. And somewhere above the overcast, the stars are burning steadily. A turn is a controlled departure from straight flight, in which the aircraft trades a fraction of its lift for the centripetal force needed to change direction. In level flight, the lift produced by the wings acts straight upward, balancing the weight of the aircraft. Note when the pilot banks the aircraft, rolls it so that one wing is lower than the other, the lift vector tilts with it. The vertical component of the tilted lift still acts upward to partially balance gravity. The horizontal component acts sideways, toward the center of the turn, the centripetal force that curves the aircraft's path. To maintain altitude in the turn, the total lift must be increased to compensate for the fact that only a fraction of it is now acting vertically. The pilot pulls back on the stick, increasing angle of attack, increasing lift, and increasing the load factor, the G, on the aircraft. A turn at 60 degrees of bank requires 2G to maintain altitude. At 70 degrees of bank, approximately 3G. At 80 degrees, approximately 6G. The relationship is not linear. The load factor required to maintain level flight in a banked turn increases steeply as the bank angle approaches 90 degrees, where no amount of lift can balance gravity because the lift is acting entirely sideways. The tightness of the turn is determined by the turn radius, which is governed by the aircraft's speed and the centripetal acceleration. The G, it can sustain. At higher speed, for the same G, the turn is wider. At lower speed, for the same G, the turn is tighter. The speed at which an aircraft can pull its maximum structural G, the corner velocity, produces the minimum turn radius for that aircraft. Below corner velocity, the aerodynamic limit applies. The wing stalls before maximum structural G is reached. Above corner velocity, the structural limit applies. Maximum G is available. but the turn radius increases with the square of the speed. For a modern fighter at corner velocity, which might be around 350 to 450 knots, depending on the aircraft, the minimum turn radius is a few hundred meters. At that radius and speed, the pilot and aircraft are pulling close to maximum G. The turn is as tight as the physics allows, and the energy state is declining as the turn consumes kinetic energy to produce centripetal force. The sustained turn rate, how many degrees per second the aircraft can turn while maintaining constant speed and altitude, is the performance metric that determines how quickly a fighter can reposition in a close-range engagement. Instantaneous turn rate, the rate achievable by trading energy for a brief interval, is higher than the sustained rate, and the pilot managing the engagement must choose when to spend energy for instantaneous rate and when to conserve energy for sustained capability. All of this happens at a speed and in a spatial scale that compress the decision time to seconds. The physics does not wait for the pilot to be ready. The turn is either correct or it is not, and the aircraft is lighter by however much fuel the maneuver consumed, and the geometry is whatever the physics dictated. The F-35 was built on the premise that in modern air combat, what you can see matters more than how fast you can fly. This is a departure from the philosophy that shaped aircraft like the F-22, the aircraft built for supreme kinetic performance, for speed and climb and maneuver. The F-35's designers accepted that the aircraft would not match the F-22's speed, its ceiling, its sustained turn rate. What the F-35 would do instead is see more, sooner, more completely than any adversary, and share what it sees with every other platform in the fight. The distributed aperture system is the most striking embodiment of this philosophy. 6 infrared cameras are mounted around the F-35's fuselage in positions that together provide complete spherical coverage, 360 degrees in every direction, including directly below. Their feeds are merged by the aircraft's computers and projected onto the pilot's helmet-mounted display, which is linked to the pilot's head orientation. The pilot looks down through the floor of the cockpit and sees, in their visor, the infrared image from the camera mounted below the aircraft, the ground passing below, as if the cockpit floor were transparent. And the pilot looks backward and sees what is behind them. The aircraft has no blind spots for the pilot's visual field. The sensor fusion goes beyond the distributed aperture system. The F-35's onboard radar, the infrared search and track system, the electronic warfare receivers, and off-board data from other aircraft, from ground-based radars, from satellites, all feed into a single integrated picture that the aircraft's computers assemble and present to the pilot as a coherent view of the battle space. The pilot does not receive individual feeds from individual sensors and construct a mental picture. The aircraft constructs the picture and presents it. The F-35 can fly with its own radar completely silent, receiving data from other F-35s through the multifunction advanced data link, rather than transmitting on its own radar, so allowing it to build a targeting picture of the airspace around it, without omitting anything that an adversary electronic warfare system can detect. It hunts with borrowed eyes, contributing its own sensor data to the network while remaining electronically dark. More than 1,000 F-35s have been built as of early 2026. 14 nations operate them. The aircraft has flown combat missions in multiple conflicts. Its development cost exceeded $400 billion, the most expensive defense procurement program in history. The F-22 clears the sky. The F-35 exploits it. Two different aircraft, two different answers to the same question. How do you win when the adversary is trying as hard as you are? One answer is to be faster. The other is to see further. Both answers are currently parked on American military flight lines. Waiting. Soar above 50,000 feet. The sky is a color that has no precise name. It is darker than the blue of the daytime sky seen from the ground. Darker even than the blue of a sky seen from a mountain summit on a clear day. At 50,000 feet, the bulk of the atmosphere is below the aircraft. Roughly 95% of the atmosphere's mass sits below 60,000 feet. And the sky in the upward direction is a deep blue-violet that grades through its darkest point toward the black that begins to be visible at the zenith if you are high enough and the conditions are right. The horizon at this altitude is different from any horizon visible from the surface. The geometric horizon is farther away. At 50,000 feet, the distance to the visible horizon is approximately 280 miles. The curvature of the Earth is detectable in the arc of that horizon, not as the dramatic curve of the orbital photographs, but as a subtle, persistent bowing of the line where the sky meets the Earth, visible if you are looking for it. The temperature outside the aircraft at cruise altitude in the stratosphere is approximately -57 degrees Celsius at the standard tropopause, and colder above that. The stratosphere does not cool with altitude the way the troposphere does, but the temperatures are already extreme. The outside air is not breathable, not because of its composition, which is still approximately the standard nitrogen-oxygen mix, but because the pressure is too low. At 50,000 feet, the atmospheric pressure is approximately 1/10 of its sea level value, and a person exposed to this environment without a pressure suit would lose consciousness within seconds. The F-22's cockpit is pressurized to the equivalent of approximately 8,000 feet. Comfortable, breathable, the pilot in shirt sleeves inside their G-suit and flight suit, working in a cabin environment that the environmental control system maintains at livable temperature and pressure, regardless of the conditions outside. The aircraft's skin is at the temperature of the stratosphere. The cockpit inside it is habitable. What the pilot sees outside is the boundary between two worlds. Below, the weather systems, the cities, the ocean, the land, the operating environment of everything that breathes and lives on the surface. Above, the increasing vacuum, the unfiltered solar radiation at the beginning of the space environment that starts somewhere above, the boundary between atmosphere and nothing marked by the darkening sky. The aircraft is between, not in space, not at the surface. In the thin, cold layer where the atmosphere gives out, and the world below becomes visible as a surface rather than a place. Flying at the edge of where engines can breathe. Above almost everything. Below almost nothing. The last minutes of a fighter sortie are the reverse of the first, in the same way that putting something down is the reverse of picking it up. The same actions, the same forces, but running in the opposite direction. The aircraft descends from altitude. The throttle comes back. The airspeed, which at cruise altitude in level flight may be 400 or 500 knots, begins to reduce as the aircraft descends into the denser air of the lower atmosphere. where maintaining the same thrust setting produces the same power but against significantly more drag. The pilot works through the descent checklist. Fuel state confirmed, aircraft systems checked, airspace clearance obtained from the approach control facility that is managing the flow of aircraft into the airfield. At the initial approach, fix, the point in the sky where the approach procedure officially begins. The aircraft is typically between 10,000 and 15,000 feet, at a speed appropriate for the beginning of the landing configuration sequence. The landing gear comes down, 3 large assemblies folding out of their wells in the fuselage and wings, so locking into their extended positions with the green light confirmation that tells the pilot they are down and locked. The flaps extend, the trailing edge high lift devices that increase the wing's camber and surface area, producing more lift at lower speeds, reducing the speed at which the wing can sustain the aircraft's weight. The aircraft is transforming. The machine that flew at Mach 1.5 20 minutes ago is becoming a slow, heavy, carefully managed aircraft, flying an approach at 150 knots. Every control input deliberate and conservative, compared to the aggressive maneuvering of combat or high-speed transit. On aircraft equipped with a drag chute, the deployable parachute that some fighters use to assist braking after touchdown on shorter runways, the chute system is armed for deployment on landing. At touchdown, the chute deploys automatically or on pilot command, the parachute inflating behind the aircraft and providing additional deceleration force alongside the wheel brakes, stopping the aircraft in the distance the runway provides. The touchdown itself is a specific event with specific expected characteristics. The threshold crossing at the correct speed and height, the flare that arrests the descent rate just before the wheels meet the runway, the nose wheel steering and differential braking that keep the aircraft on centerline as it decelerates down the runway. The aircraft stops. The chute, if deployed, is jettisoned when ground speed is low enough. The aircraft taxis off the runway at the first available turnoff. The day is done. The mission is over. The aircraft rolls toward the flight line. The engines are still running. The canopy is still closed. But the speed is walk-in pace, and the sky is behind it now, and the concrete is beneath, and the ground crew are already walking out to meet it. The hangar at night belongs to the maintenance crews. The flight line has been quiet for hours. The last sortie landed before dark. The pilot debriefed. The ground crew completed their post-flight checks, and the aircraft were towed into the hangar for the overnight work that keeps them ready for tomorrow's flying schedule. In the hangar, the overhead fluorescent lights are on. The operational aircraft do not sleep in darkness. They sleep under the white light of people working on them. The maintenance crews move around the aircraft with the organized purpose of people who know exactly what they need to do and have done it hundreds of times. One crew has an access panel open on the engine compartment, the turbine stages visible under the inspection lighting. Another is at the undercarriage, checking the torque on the wheel assembly after a harder than usual landing. A third is running through a built-in test of the avionics system, the cockpit displays cycling through their diagnostic sequences while the aircraft sits motionless on the hangar floor. The cockpit is open. The canopy is raised on its hydraulic actuator, the ejection seat occupying its position in the cockpit, the seat's mechanisms in their armed state, the ejection handles connected, the initiators in their firing circuits, the seat ready to function if it is called on. The Martin Baker seat does not rest. It is always armed, always ready, the precaution that the aircraft maintains, even when the aircraft is not flying. The engines are cold now. The metal of the airframe, which was at minus 57 degrees on the outside and heated by the engine's exhaust on the inside during the flight, has equilibrated to the hangar temperature. The thermal gradients that cause a metal structure to tick and crack as it cools, the sound that returning aviators describe as the aircraft talking to itself, have settled. The airframe is quiet. You have spent tonight inside one of the most capable machines the human species has ever built. You know that the turbine blades of its engine operate above their own melting point and survive by the same principle that Goddard discovered for the rocket combustion chamber, the propellant cooling the wall it is about to burn. But you know that the afterburner uses the half of the ingested oxygen the main combustion must leave behind, and that the shock diamonds in the exhaust plume are pressure oscillations made visible. You know that Mach 1 is a transition, not a wall, and that Chuck Yeager crossed it on October 14th, 1947, with 2 broken ribs and a broomstick handle. You know that 9G weighs 9 times everything: the pilot's blood, the pilot's arms, the pilot's eyeballs, and that the grey curtain comes in from the edges before the darkness does. You know that the F-22 can fly faster than sound without the afterburner, that its radar cross-section is the size of a marble, and that 187 of them were built and none were ever sold abroad. You know that a carrier catapult delivers 165 miles per hour in 2 seconds, and that the arrested landing reverses it in the same time, and that naval aviators call it a controlled crash, not because it is out of control, but because there is no softness in it. You know John Boyd's phrase, "Energy is life." Before you close your eyes tonight, one small thing that means everything to this channel. Please hit the like button and subscribe if you haven't yet, because tomorrow night we will be here again with another story built exactly for this hour. Your place is kept, but for now, the hangar is lit, the maintenance crews are working, the ejection seat is armed, the engines are cold and the airframe is quiet, and outside the hangar, the flight line is dark and still, the aircraft that flew today at rest, ready for tomorrow, already being prepared by the people who make it possible for anyone to fly them at all. The night shift continues. The aircraft waits. The work never stops. Sleep well.